Thank you very much, Jousef, for inviting me in this course and in this presentation. So good morning. Sorry, it is the morning for me. Probably it is the afternoon for you. I don't know where you are on Earth, but so good morning, good afternoon. As Jousef said, I am Dominique Madier. So I am an FEA engineer, and my FEA is a passion for me, and I love to do FEA, but I love also teaching FEA. So I'm going to try to do that during this presentation, and I want to cover a vast topic, which is an overview of the good modeling practices in FEA, in order to get correct results with your simulation. You know that the finite element method, because here it is what we're speaking about, it is one of the most used simulation technique in engineering. So I think I'm going to start with sharing my screen. It's better to do that now because I see that I don't share it now. So let's do that. And I think it's correct now. I share my screen. So yes, as I said, it is a very popular method used in engineering for simulation. And the modern FEA software makes doing finite element analysis, the simulation, I should say, very easy, and even too easy, according to me. And this is because you have a nice graphical user interface that guides you through the process. Okay. I think it seems that the sharing is not working. Okay, that's very strange. It seems that the sharing is not working, but
well, I can see a screen, Dominique.
Okay, sorry. I have sorry. So as I said, this is because you have a nice graphical user interface that guides you through the process of creating, solving, and post-processing a finite element model. Okay, it seems that there is no need to know much about FEM due to this interface, but it is wrong, okay, in reality, because FEA is complex and the FEA analyst needs to learn a lot of things about FEA. So FEA analyst must gain knowledge of in many areas. FEA is a very, very powerful and versatile tool, but only if you use properly, okay? And the problem is the FEA software itself will always generate accurate answers. However, without proper guidance, the new user will easily make almost every possible mistake. Okay. Today, I want to share with you few generic guidelines, and it's very important. It will stay generic. I cannot enter in details because it takes many hours, okay? But just want to share with you few generic guidelines which will help you creating the correct FEA. So here it is the agenda for today. I want to start with the presentation of what is the good modeling practices approach. Then I will present a few guidelines related to the three phases of FEA. First, building the model, then solving the model, and finally, post-processing the model. There is a lot of material in this presentation, so if you wish, I can send a copy to Jousef of this presentation, and he will share that with you. Okay, so let's go with the details. So the objective of an approach incorporating the good modeling practices, it is to use FEA intelligibly, okay, and not as a black box. Even if from a solving point of view, it is one. I mean, it is a black box, okay? So here are the 10 points you need to consider in order to make sure that your FEA will produce an accurate result. First, you need to understand the physics behind your problem. You understand that if you simulate a solid mechanics problem or a heat transfer problem, you need to understand this physics, okay? Otherwise, you won't be able to do the simulation. You need to know what you are looking for. You cannot run the simulation like that without knowing what you are looking for in terms of results. You need to have an idea of what the results should look like in advance, okay? in terms of behavior. You need to understand the behavior of the elements in the library of your FEA software. You know that your FEA software will come with a certain elements of a certain library of elements. You need to understand them before to build the simulation. You need also to select the right elements for the task you have for the simulation. And you need also to perform the correct discretization. By discretization here, I mean the proper, the meshing, okay? The proper mesh density and the good quality of the mesh. You need also to apply the correct boundary conditions. And here, by correct boundary conditions, I mean constraints and loading. And you have to know that it is one of the most complex tasks of when generating a simulation, defining the boundary conditions. You need also to understand the effects of your assumptions on the response of your model. And this point, the point 9, is related to the point 8. You need to know how to modify the model in order to improve its accuracy. So it is the reason why you need to understand the effects of your assumptions. And there are many assumptions you will have to do in order to build your simulation, your FEA. And finally, you need to keep a critical eye on the results. And you need to understand the critical outputs, because the FEA basically will always give you a result, but not necessarily the results corresponding to the reality. Because if you don't submit the right system of equations, you will obtain a result, but probably that the result will have nothing to do with the real problem. Okay, so like I like to say that why the FEA software vendors do their best to help the users become FEA experts, you must ultimately understand how to properly use the tools without treating FEA simply as an extension of CAD. And I say that because similarities between CAD and FEA are limited to geometry at best, okay? And there is also a risk of assuming that the FEM's accuracy depends only on precise geometric representation. The problem with this assumption is that many other factors may be ignored, such as the selection of the right elements, the definition of the right boundary condition, the selection of an appropriate material model, the convergence study, and so on. A lot of different factors which will influence the result. So FEA, it's not only CAD, it's not only a good representation of the geometry. Okay, so always keep in mind that FEA is complex. Okay, and geometric accuracy and attractive color plots alone do not guarantee high quality analysis. So let's start with the good practices when we build the model. First, it's a question of planning the work and keep it simple, okay? I like to say when I teach FEA strategy that developing an FEM, it's like playing chess. And believe me, it's right, it's true. To develop a reliable FEA, you must first anticipate the problems, then predict the behavior, and finally adapt your strategy. We know that anticipating the potential issue when building a complex FEM, it's not easy. And you will face issues, you will face problems when you're going to build your model, okay? So it is why planning, it is the key. Without planning, you may encounter problems you won't be able to solve without diminishing the intrinsic quality of your model. So the main objective of an FEA is to understand the system. So you need to define the goals of the simulation as precisely as possible at the beginning, even before starting your FEA software, before starting your pre-processing software, I should say. So to help you in defining the goal of your simulation, always try to answer the following questions before to start modeling. what should be captured by the FEA, which quantities are to be calculated, which conclusions are you going to draw from the simulation, and what is the required precision of your calculation. The most common error made in FEA simulation is setting up a simulation without answering this question. You know, they are very simple 4 questions, and you should do that before to start modeling, as I said, okay? And what I want to say it is you cannot start the simulation without having a clear goal in mind. Never set up a model to see what happens or to see how stresses are distributed, okay? A precise definition of all the objective is very important for defining the modeling techniques and the solution you will use, because you know that many solutions are available to you: linear, nonlinear, static, dynamic. I will come back to that later. And this will influence many of the assumptions you will make during the building process. For example, different modeling techniques are used to model linear and nonlinear problems. You know that. There are also different modeling techniques for capturing a peak stress in a particular region of a component versus just the stiffness of the whole component, for example, or just knowing the loads instead of the stress. Modeling techniques are different depending on the goal of the simulation. So when you build your model, keep it simple. Keep the model as simple as possible at the beginning of, okay? For example, if you only need to know whether a yield stress is exceeded somewhere in a metallic component, for example, it is much easier to perform an elastic calculation and check the von Mises stresses with the post-processor. Don't need to go with a full nonlinear solution if you just need to know if you exceed the yield stress. So at the beginning of the project, a design is usually preliminary and even incomplete. So at this stage of the preliminary design, the FEA analyst supports the design team to define the concept, okay? At this point, it is best to keep the FEA simple. It will be easier to implement modifications and to run a threat study, for example. And it is what we're doing at the preliminary design, okay? But take care not to oversimplify the models to the point that the critical effects are missed. It's very important to have that in mind. At the beginning of a project, use coarse mesh with simplified modeling technique. It is the key. Okay, once the design is mature or enter the final phase, okay, the FEA analyst must validate the concept. So this final verification requires more details like mesh refinements, more detail in the loading, modeling fasteners, for example, in solid mechanics. Okay, so at this stage, at the final phase, you will go with more refined FEM. But when you are going to add complication in your model, do that step by step. Setting up the model in steps has two advantages. If errors occur, okay, it is much easier to find out what caused the problem or the errors. And understanding the behavior of the system is easier this way because you understand which addition caused which change in the model behavior. When running a finite element analysis, one of the first decisions you must make, it is about the type of analysis you're going to run. The objective is to define the type of analysis required to capture the real effects. Okay, it is what I call select the right solution. Okay, so you will have to choose between a static, buckling, model, dynamic, linear, non-linear simulation. You know, the FEA software nowadays, they are so versatile that we can do a lot of many type of analysis. So the first question is static or dynamic. Okay, You have to know that dynamic simulations require the presence of inertial forces and changes in kinematic energies, okay? But if inertial forces are irrelevant, run a static solution. It will do the job. If the loading is constant over a relatively long period of time, and if the loads are applied gradually, the static analysis will give you the right answer, okay? My rule of thumb in order to do this assessment between static or dynamic. If we consider that a simulation is static, if the excitation frequency is less than 1/3 of the lowest natural frequency of the structure, okay? To obtain the natural frequency, you need to run, obviously, the model analysis, okay? The static analysis won't give you the answer in terms of natural frequency. So you will need to run the normal mode analysis. I will come back on that later. So a dynamic analysis itself needs, you define the damping to obtain the good results. You have to keep that in mind. So when you run the dynamic analysis, you have to make sure you can estimate or measure the damping of the structure and the system you want to analyze. Then you have to decide if you run a linear or a nonlinear solution. If you are planning to run a nonlinear analysis, you should answer a few questions to decide if you really need or if the linear analysis will do the work, okay? Because sometimes it is the case. Sometimes the linear analysis is perfect, and it will answer the questions. You have to keep in mind that nonlinear analysis requires more resources in terms of disk space and computing time. So it is important to ensure that it is really necessary. I like to say that it is better to run a nonlinear analysis unnecessarily than to ignore the nonlinear effects, okay, when it is required, because this can lead to serious design errors. If you run a nonlinear solution while there is no nonlinear effects, the nonlinear solver will give you the same answer as the linear run, okay? However, if your structure exhibits significant nonlinear effects, the answer using the linear solution will be wrong. So here are the questions, the typical questions I like to ask myself in order to decide between linear and nonlinear. Is the stiffness of the structure changing when a loading is applied? If it's no, if the answer is no, it is a linear. If the answer is yes, it is a nonlinear solution. Are the strains in the model less than 5%? If it is yes, it is a linear. If it is no, it is a nonlinear. Are the loads and boundary conditions constant in magnitude and direction during the analysis? If yes, the linear run will give you the right answer. If no, you need a nonlinear. Is the behavior of the structure independent of load history? If it is the case, if it is independent, the linear run will give you the right answer. Otherwise, you will need a nonlinear. Are the stresses of the model exceeding the proportional limit? It is the typical case of a nonlinear material. If you don't exceed, the linear analysis will give you the right answer. Otherwise, it is nonlinear. And finally, it is the question of, it is a nonlinear geometric question. Is the structure exhibit stress stiffening? Okay, for example, the tension bending coupling. And in this case, if the structure exhibits stress stiffening, it is a nonlinear. You need to go nonlinear. Otherwise, the nonlinear solution will give you the right answer. So here are the typical questions I like to ask myself in order to decide if I go linear or nonlinear. Also, if you are interested to capture the linear stability of your structure, you have to run a linear buckling analysis. But you have to verify that your problem is working in the small displacement domain and that yielding does not occur, because in that case, you will have to run a nonlinear buckling solution. And keep in mind that the linear buckling analysis will compute only the buckling factors with the associated mode shapes. And it will tell you only if your structure is stable or unstable, or not stable, okay, unstable, sorry, with the associated resolve factor, the associated margin of safety. Not more. If you need the displacements or stresses at buckling, or you need to capture what will happen after buckling, what we call the post-buckling, you need to run a nonlinear buckling analysis. Finally, you need to define if you need to run a model analysis, as I told you at the beginning of the presentation. You need to run the model analysis if you need to define the natural frequencies at which a structure tends to vibrate in order to avoid resonance, but also to define if your loading is less than 1/3 of the first natural frequency, okay? So a typical usage of model analysis, it is first capturing the natural frequencies with the associated mode shapes to avoid resonance, in order to check if you have resonance. The second usage of the model analysis, it is define the behaviors of a structure under dynamic loads before to run a dynamic analysis. It will tell you, the model analysis, the results of the model analysis will give you a lot of clue about the dynamic behavior of the structure. And finally, the model analysis can be used to identify possible modeling mistakes, like missing connections between components, constraint incorrectly defined, stuff like that. So it's a very, very powerful solution. Also, when we build a model, we have to choose the element type. And choosing the element type is often the crucial step in creating a finite element model, okay? Never accept the default choice of your program without thinking about it. It's very important, okay? Carefully check which types of elements are available with your FEA package, okay? And make sure you understand how a finite element simulation is affected by the choice of the element type. It means that you should understand the concept of element order and integration point, what we call also the ghost points. And you have to learn the most common errors caused by an incorrectly chosen element, because many problems can occur due to the fact that you select the wrong element. Something like, for example, shear locking or glassing, or few examples. So to select the right elements, you need to predict your structure behavior. You don't use FEA in order to predict the behavior, okay? You have to know the behavior in order to do the right assumption to build your model. It is very, very important, okay? So it means that you must understand the load path in your structure to be able to select the right elements. As I said, you don't use FEA to predict the behavior of your structure, okay? You do the opposite. And you must be able to predict the behavior of your structure to build a reliable and accurate FEA. If you do not have a fairly good idea of how the structure will behave, you won't be able to select the right elements for your simulation, okay? Very important to have that in mind. So to make sure you select the right element, you should experiment your library of elements before to use it, okay? Because if you are not familiar with an element, you won't be able to make a decision on the choice, okay? So you have to experiment it by doing very simple test model, okay? With simple axial loading, simple shear loading, simple bending loading, and experiment the very, very simple cases, plate, cantilever beam, stuff like that, and observe the behavior associated with each element. This practice will give you a better understanding of an element's capability and limitations. Very important. The capabilities and the limitations before using those elements in a large production model. So here are a few guidelines for a correct element choice. First, use 2D shell elements instead of 3D solid elements for thin wall structures. Okay, what are thin wall structures? Thin wall structure or structure having a width to thickness ratio greater than 10:20. Okay, in that case, use 2D shell elements, not 3D solid elements. When you use 2D elements, make sure you use the correct formulation. Here, by formulation, I mean shell or membrane, because shell and membrane, they look very similar, but they behave differently. Just because the shell can react and transfer membrane loads, the shell, sorry, yes, can transfer membrane loads and out-of-plane loads, while the membrane can only transfer in-plane loads, the membrane loads, okay? Do not use fully integrated first-order elements if bending occurs in your structure. In that case, prefer the reduced integrated element. In contact problem, the first-order elements can improve the convergence drastically. If elements distort strongly, it happens sometimes in case of large displacement, the first-order elements are better than the second-order elements. Avoid the triangular and the tetrahedral first-order elements, the 3 and the 10-4 elements, because they are too much stiff, okay? Especially in bending, very important. They produce wrong results in bending. And for the 3, you can use them, but only in transition regions, far from the regions of interest. For 3D solid meshing, prefer X element, the X8 or X20. If the X meshing is not possible, and it can occur for very, very complex geometries, even if the preprocessing software are improving a lot and permit us to mesh in X, sometimes it's not possible. So in that case, prefer the TET10, okay, second order tetrahedral elements. They give very good results in critical regions when the mesh is converged. But do not mix elements with different orders, okay? An X8 with an X20, for example, or a TET4 with a TET10, okay? But you don't have to use TET4, TET10 only. This can cause overlaps or gaps forming at the interface, possibly not shown by your post-processing software. When incompatible elements in terms of degrees of freedoms are used, because you know that all the elements, they don't have the same capabilities in terms of transferring the degrees of freedom, so you can have incompatibilities in the same models when they are connected together. Make sure you manage the incompatibility at the interface using extra element or interpolation rigid body element. It's a typical modeling technique because for sure we use incompatible elements, but we make them compatible using extra elements or rigid body elements, interpolation rigid body element. Even if it's possible to mix reduced and fully integrated elements of the same order, it is not recommended, okay, practically speaking, because they differ in stiffness and spurious stress or strain discontinuities may occur. Understanding meshing when we build the model is very important. It is a very important part of the simulation process, okay? Because it will drastically influence the results obtained with your simulation. You have to keep that to keep that in mind, okay? So let's have a look at the major guidelines for meshing. I don't want to teach you how to do a meshing for sure. I don't have time to do that today. But there are a few guidelines I want to share with you. First, a fine mesh is needed where gradients in stress and strain are significant, okay? For thin wall structures, mesh with 2D shells at mid-plane usually. In composite, sometimes we mesh at the OML with offset. But thin wall structure, 2D shell. A preliminary solution with a coarse mesh may help to identify the regions where a greater mesh density is required, because it is a common modeling technique to do that. We mesh coarse in the regions where the stress are not very high, where we don't have the stress concentration effects, and where in the region where we have the stress concentration effects, the peak stresses, we refine the mesh, and in those regions we converge the mesh. Keep in mind that the required mesh density depends on the quantities you want to extract and on the required precision. For example, displacements are often calculated more precisely than strains or stresses because the strains involve derivatives. Okay, check the shape and the size of the elements. The inner angles should not deviate too much from those of a regularly shaped element. Here I'm talking about the mesh quality check. Okay, so your FEA post-processing software is able to do this check. Okay, it's very important to avoid badly shaped elements, especially in regions where high gradients occur and in regions of interest. If you use local mesh refinement, the transition between the regions of different element size, it should be smooth. Okay, as a rule of thumb, adjacent elements should not differ by more than a factor of 2 or 3 in their area or volume. Okay, if the transition is too abrupt, spurious stresses may occur because a region that is meshed finer is usually less stiff. Okay, so always keep in mind that the transition need to be smooth. For the mesh transitions, never create a mesh transition in a region where there is a stress gradient. Okay, never create a mesh transition also in a region of interest, because the mesh transition region is not, you cannot use it. Okay, so if there is a region of interest, you don't put the mesh transition there. In this region, you create the refinement and you move away the transition. Also respect the physical interfaces, okay, when you create those transitions. If you wish to capture the peak stress or strain in a region with a stress concentration effect or high stress or strain gradient, you must perform a convergence study to define the appropriate mesh density. Because most of the time at the beginning, when we develop the model, we don't have the test results, okay? So we cannot rely on a test result in order to validate the mesh density. So you need to conduct the convergence study in order to make sure that you capture the maximum stress in the region of interest, in the region where we have a peak stress around the hole, for example, as illustrated here on this example. So when performing the mesh refinement, you should prefer a local refinement instead of a global element size reduction. This approach permits to limit the number of degrees of freedom. And it's very important because always keep in mind that the computing time is proportional to the square of the number of degrees of freedom. I know that we have very powerful computers now, and we can run models with a lot of degrees of freedom, but you make sure that you don't generate degrees of freedom for nothing, okay? 3 last guidelines about meshing. Avoid the mid-side to corner node connections between elements, okay? The adjacent elements should have connected mid-side nodes. Avoid also back-to-back triangles. Do not connect 2 triangle elements and avoid triangular elements at the edges of O's, for example. Do not create mesh transitions in fillets. Make them on planar surfaces. It's very important. During the process of creating an FEA, defining the boundary conditions, as I said at the beginning of the presentation, is the stage at which many engineers, many analysts make incorrect assumptions because it is difficult. The topic of boundary condition is less understood by FEA beginners, but it is not uncommon for experienced engineers to have also difficulty to properly defining them, okay? Boundary conditions have a major impact on the result of an analysis. And a small mistake when defining them can make the difference between a correct and an incorrect simulation, believe me. So let me share with you a few guidelines about boundary conditions, defining boundary conditions, okay? First, you need to use a strategy to define your boundary condition. You need to predict how the model will behave using your engineering judgment or using test results or previous analysis or all of them. But using your engineering judgment is very important, okay? So how the model will behave, it can be done by predicting how the model, will deform, because it's easy for an engineer to predict how the structure will deform under a certain loading, okay? So ensure that the set of boundary conditions here, I mean by boundary conditions, I mean constraints and loadings, reflect the real life. Do not apply boundary conditions which are not related to the real life. Make sure that all parts of the models are constrained so that no rigid body motions are possible. It is the first error when defining boundary conditions. If you do not constrain all the rigid body motions, the 3 translation and the 3 rotations, definitively your solver won't be able to give you a solution. After calculating the model, take time to ensure that nodes were constrained as you expected, using your post-processing software. And it is at this stage where you are going to compare your prediction, the prediction you have in your mind in terms of deformation, with the results. Okay, and here I don't say that you need to predict what is the value of the deformation, because sometimes, most of the time, it is very difficult. Okay, but the shape of the deflection, as an engineer, using your engineering judgment, you are able to predict that. Okay, so it is a clue that the boundary conditions are correct. If the loads are changing of direction or magnitude during the simulation, you will need to run a nonlinear geometric solution. Also, in order to define your strategy for defining the boundary conditions, predict the load path before running your model, okay? And compare this prediction, the load path prediction, with what you obtain with the solver, with the simulation. And always trust your engineering judgment, okay? Also, make sure you don't generate an over-stiff or under-stiff problem, okay? The boundary conditions, usually, they generate singularities. So keep them far from the regions of interest, okay? Don't put the boundary condition close to the zone of interest. Put them far away. So probably that you will need to do a bigger model than what you need in order to do your stress assessment. Also, in your strategy in defining boundary conditions, different boundary conditions, check at rigid body motions and mechanism. It's a clue that you have a problem with your boundary conditions. So here, to conclude with boundary conditions, let me share with you the 7 questions you should answer to successfully defining your boundary conditions. As I said before, at the beginning of the presentation, there is more to say about boundary conditions, but I don't have time here. So I just want to share with you my 7 questions. The first question you have to ask yourself, where are your structure supports in the real life? Why? Because you have to replicate the real life. If you don't know what is the real life, you won't be able to model it, to model it and to define your boundary conditions. What are the degrees of freedom of your structure in reality? Because it is the same. You will have to replicate the degrees of freedom of your structure with your simulation. You need to know them before to start defining the boundary conditions. If you apply a certain set of boundary conditions, ask yourself if you allow or restrict the degrees of freedom that exist in the physical system you are modeling. What are the loads applied in the structure? Okay, if your structure is subjected to a pressure effect, you will not apply enforced displacement. You will apply this pressure effect. What types of loads are applied to your structure in the real world? Again, always refer to the real world. The other question you need to ask is, can you remove some parts of your model structure and replace them with boundary conditions and still produce a realistic representation? If not, if the answer is no, it means that you will have to model more components in your system to make sure that you capture the right interfaces, the right boundary conditions between components, and you will be able to apply the right constraints and loadings. Okay. Finally, does your structure exhibit contact between some parts? Contacts, it's a typical boundary condition, okay, because it's also a constraint between some parts. So you need to know before to start the modeling process if some parts will exhibit contact between themselves. So to conclude with the section about building the model, here I want to give you the 14 questions that I like to answer before to begin the modeling process. Have you clearly identified the model's goals? Which solution do you plan to use? And is it consistent with your problem? Static, buckling, model, dynamic, linear, nonlinear. Do you trust the geometry you plan to use? And can you change it if necessary? Can you justify your choice of elements? Your knowledge of the library of elements here is very important. Which boundary conditions will you apply to your model? Why did you select them? Do you understand perfectly the loading you will apply in your model? Have you identified the major load path in your structure? Are you able to anticipate the response of your structure? At which locations in the model do you plan to extract the result? Sorry. And which accuracy of results do you require? It will influence a lot, for example, the meshing. Have you identified all the modeling techniques you will use to build your model? Have you identified discontinuities in the structure, the structure you wish to model for sure? And have you identified all the capabilities and limitations of your model? Because your model will have limitations. Your model won't be able to answer all the questions, but you need to know that. Do you expect, finally, any potential sources of nonlinearity? If you are not able to answer all the questions there, do not start the modeling process. So let's talk about solving the model, okay? And first, I want to talk about the log file. Even if your model is solved without any convergence problems, look at the log file. The log file, it is written by the solver, and this log file contains warning messages. They may be harmless, but they may indicate some problem in defining your model. Convergence problems are usually reported by the program, by the solver, with warning or error messages. You can also see that your model has not converged if the final load increment in the history is not the last load increment you specified in the model definition, okay? There are two reasons for convergence problems. First, the solution algorithm may fail to find a solution, even if a solution of the problem does exist. In this case, modifying the solution algorithm may solve the problem, okay? On the other hand, the problem definition may be faulty, so that the problem is unstable and does not have a solution. It is the reason why you obtain this error. So let's talk about the convergence problem. Use a post-processing software, sorry, okay, in order to identify the nodes with the largest residual force and the largest change in displacement in the final increment before the divergence. And very often, but not always, this tells you where the problem in the model occurs. So it's a very simple check. Okay, you just do a displacement plot of the last converge load increment. The definition of the load increments also for a nonlinear solution is very important. If, for example, you abruptly change the applied load at a certain point of the load increment, the incremental process may not capture the exact point at which the change will occur. So define the load steps to ensure that the moment of the abrupt change corresponds to a large load increment in the simulation is very important. It will improve convergence because it allows to control the increments at the moment of abrupt change. With the modern FEA software, if the convergence is not obtained by the solver, the last load increment is automatically reduced by doing a cutbacks, okay? Usually the last load step is cut in half. So the program stops if the load increment is too small or if the convergence problems persist even after several cutbacks of the load increments. So your FEA software will print you a message, okay, in the log file for that. However, these messages themselves, they do not tell you anything about the reason of the convergence problem. So to find the cause of the convergence problems, you need to look at the solver log file in the increments before the final error message, okay? And usually there are a lot of very interesting messages in the log file for each load increments. So you will see warnings that tell you what kind of convergence problem occurred. For example, the residual force is too large. The contact algorithms did not converge. The load increments were too large. Have a look at the last converge load increment, as I said before. Frequently, the large changes in some quantity may indicate the location of the problem. Personally, I like to look at the displacement. So with your post-processing software, it's very easy to do that for each load increment to have a look at the displacement. If the first load increment does not converge, set the size of the first increment to a very small value. If the problem persists, it means that the model itself is unstable due to missing boundary conditions or an initial overlap of contacting surfaces, for example. To find the cause, as I said, of the convergence problem, simplify your model step by step. Make sure that the model is properly constrained, okay, all the rigid body motions are removed, and use simpler material laws. For example, switch to elasticity, for example, instead of plasticity. Switch up the nonlinear geometry. Remove all the external loads step by step, okay? It's an example of simplification you can do in order to catch the problem. If the problem persists, try to create a minimum example. This approach has several advantages. It is because the minimum example is easier to analyze. And it needs less computing time, okay? When so you can try a few things faster. But also you can easily share your model with others in order to obtain help. To conclude the solving part, let's talk about solution parameters. If your solution algorithm does not converge for numerical reasons, the following guidelines here may help, okay? But they are useless if there is true model instability. Finite element programs, they use default values. And you need to learn those default values related to your FEA software, okay, before to go with your nonlinear analysis. So they use default values to control the Newton-Raphson iterations. If no convergence is reached after a fixed number of iterations, as I said before, the load step is cut back. In strongly nonlinear problems, these default values, they may be too tight. It doesn't work, okay? For example, some FEA software, they cut backs on the load increment if the Newton-Raphson algorithm does not converge after, let's say, between 4 and 5 iterations. Setting this number to a larger value is often sufficient to reach convergence. Personally, I like to set this parameter to at least 25 when I'm using my FEA package. I'm using Nastran. If due to the cutbacks, the load step becomes smaller than a predefined minimum value, the simulation stops with an error message. This minimum size of the load increment can also be adjusted, okay? If the convergence cannot be obtained with the Newton-Raphson algorithms, and it can occur for buckling problems, for example, you can switch to the arc-length method, like a Crisfield or a Rix algorithm, okay? It will improve the convergence method. So the arc-length method, Crisfield and Rix, usually they are used for nonlinear buckling, while the Newton-Raphson method are used for nonlinear static. So the last step, yes?
I'll interrupt you because we start the Q&A if that's okay. How many slides do you have left?
No, I have like 20 slides left.
Okay, because we have 10 minutes now left for the Q&A. If you want to show the most important ones, because we had a question.
Yeah, I can do that. Yeah, for sure, I can do that. I can do that. So the most important steps, no problem, Jousef. For the post-processing stage, okay. The most important thing I want to say, it is about verification and validation. Please do not go to the post-processing of your model if you don't do the verification and validation process, okay? Because first, the verification, it is the process of defining that the computational model accurately represents the mathematical model and the solution. It verifies that the model works, the math is right, the FEA analysis is accurate, okay? So do that, it's very important, okay? So you need to do accuracy check, mathematical check for the verification. After that, you need to do the validation, which consists in comparing the result, the model, the answer of the model with a test result, okay? So you have to do that before to jump into your post-processing process. So post-processing the model, I have few recommendations there. Okay, probably that is better. We jump to the Q&A session. I'm going to share this presentation with you guys, so you will be able to download it. It's not a complete course about post-processing. Again, I cover that in my courses, but it's few recommendations, okay? So in conclusion, I just want to say you that making FEA is more than just using a software, okay? It is a matter of understanding the FEA process using the best modeling practices and knowing the behavior of the system you wish to model. It's very important. At the end of the day, you will have to use a software. But at the very beginning, you need to learn the modeling techniques. It is very important. You need to learn basic FEA theory, then the modeling techniques, and after that, how to use an FEA software, okay? So it's very important, and your engineering judgment is very important because it defines the fact that you are going to select the right modeling techniques and you are going to do the correct assumptions. As you can see here on this slide, there is a lot of things to learn in order to do an FEA analysis. But don't worry, everybody can learn FEA. It is the beauty of that. So do not trust the computers too much and ask the right questions to the solver and to the computer. And never presume that a structure will behave as a computer says. It's never the case. Okay, simulation will just assist you as an engineer. Okay, but your engineering judgment is the most important thing when you do simulation. If you need help in order to learn the modeling techniques, feel free to read my books. It's more than 600 pages about methods, guideline, modeling techniques in order to develop practical finite element analysis. On top of that, I offer you to teach you finite element analysis through my courses. I have a basic course in 17 lecture, 20 hours, and a nonlinear course in 6 lecture, 12 hours. You can have a look at that. It is available on the FEA Academy website. And again, you can join me anytime to talk FEA. It will be a real pleasure for me to talk FEA with you at the email address here on the screen and on LinkedIn. That's it for me.
That was very packed and fast, Dominique, but I very much appreciate your talk. Very good. We have 2 questions actually in the chat, actually 3, sorry. Sebastian had the first question about boundary conditions. Could you quickly explain what are boundary conditions and why are they important? I would assume they are critical, if not the most critical part of a FEA model. What do you say?
Yeah, that's a great question. Sorry, I assume that everybody knows what is a boundary condition. A boundary condition, it is like an artifact for us, okay? But it is related to reality. It is, we call that a constraint or a loading. Let's start with the constraint. The constraint, it is how the structure you are modeling is fixed. Let's say I have an object, I want to simulate this object on the ground, and I apply a force here, and I want to verify how this post, for example, will buckle, will deform under a loading like that. In the reality, this post is supported on the ground. This support is a boundary condition, okay? And I need to replicate this boundary condition in my model to tell the solver that my post cannot move in this direction, okay? So this is a very simple boundary condition. So it informs the solver how the structure interact with the environment in terms of displacement, okay, and reaction. So it can be translations, it can be rotations, it can be a combination of that, and it can be in several different regions in the model, because with complex model, we have a lot of different interactions with the environment, okay? But it can be also a loading. For example, a force at a certain point, a pressure in a plate, an enforced displacement in a certain region, a temperature in a region. It's another kind of boundary condition. And the last type of boundary condition is a contact. Because when we have a structure, a system composed of multiple bodies, those bodies can enter into contact and interact between themselves, okay, and push or disengage. It is another type of boundary conditions. So the beauty of simulation today, it is the fact that we can simulate with mathematical objects, we can simulate those different type of boundary conditions.
Great, that covers it. Next question from Walid is in the step of the discretization, which he's not familiar with. Is the finite element something called or related to voxel solvers? What is the relationship between voxels and FEM?
The relation between what and what?
A voxel-based approach and FEM.
Voxel, sorry, I don't know what is voxel.
I've only heard that in lattice-Boltzmann applications, a voxel or voxelization methods, but FEM.
So is it a question related to discretization? Do they want to know what is discretization?
Probably how the discretization is done.
Yeah, I guess, so I guess totally unfamiliar with FEM, of course, but a voxel in computer graphics is a grid in 3D dimensional space. So it's pixel. So as pixels have the 2D bitmap, voxels have sort of other position coordinates. So I was just curious if that concept is part of the discretization or not?
Okay. Okay. So you use the word grid. So it means that we are talking about meshing. In FEM, it is meshing. Okay. So meshing and discretization, it is the same. It is two words. There are two words to say the same thing. So what is the objective of the discretization of the meshing? The objective is to make the problem solvable by a computer. You know that the physics in the real life, we have real behaviors in the real life, mechanical behaviors like solid mechanics, like transfer heating, something like that. Those behaviors, they are described by partial differential equations. So you can find partial differential equations which will permit to describe the behavior of a system, of a physics. Okay. The problem with the differential equations, it is the fact that they are not solvable by a computer. The computer cannot solve a differential equation. So it is where the finite element method is coming. With the finite element method, we cut the problem into several parts: shell elements, brick elements, 1D elements. And by doing that, we transform the continuous problem into a discrete problem. And by doing that, we transform the system governed by a partial differential equation, by a set of partial differential equations, into a set of matrix equations. And it is exactly the same system, but it's a system matrix of equations. The beauty of that, it is the fact that the computer can solve the matrix equations, not the partial differential equation, but the matrix system. So it is the objective of the discretization, to transform the set of differential equation not solvable by the computer into a set of matrix equation solvable by the computer. I don't know if you answered the question.
I think it's voxel is just another word, but valid voxel or mesh is the same thing basically.
Okay, I learned something today.
Okay, two separate. Yeah. Thank you so much.
Yeah, but some people, I think there's also publications that talk about voxel-based FEM or whatnot. But if you talk about lattice-Boltzmann methods in fluid mechanics, I think they use the term voxel.
Oh, okay,
also
okay.
Grid.
Good to know. Good to know. Good to know. I didn't know that.
Yeah. There was also a question which I partially answered, which is how would you set the boundary condition if you have a plate with a hole? How far does that boundary condition have to be in order to have a realistic use case?
Yeah, that's a good question. Usually, as I said before, we don't put the boundary conditions close to the zone of interest. Here, since you are talking about a hole, correct, Jousef? We are talking about a hole. It is the question.
Correct. Yeah. So, plate with a hole.
So okay. So typically a plate with a hole. The answer is have a look at the fringe of the stress. Do a stress plot. Okay. And make sure that your boundary conditions are not in the region of the gradient. I'm pretty sure you understand what I mean by gradient, because you have a peak stress around the hole, and when you go away from the hole, the stresses are decreasing, so it generates a gradient. Okay, and when you are far from the hole, usually 2.5D, 3D, 3 times the diameter of the hole, we start to see a more constant stress field. Okay, so it means that in this region the boundary conditions are no more influent. So the answer is try to make sure that the boundary conditions are in a region where you don't have a stress gradient. Okay.
Yeah, good point. It's basically stress gradient, in other words, how the stress changes from one cell to another.
Absolutely. Absolutely.
But at the end of the day, Dominique, you would probably agree to that. You have way more experience than I have. The best way to learn about that is actually tackling use cases. So there's no way around it.
Yeah. Yeah.
Yeah. Any more questions, guys? Otherwise, we'll wrap it up. But yeah, Dominique, thank you so much. If you could send me over the slide, I'll share it with the community.
Absolutely, no problem with that. For sure, I do that. Thank you very much for inviting me.
Sure, no problem. And if you have any questions to Dominique, you can find him also in the community.
Yeah, do not hesitate.
Thank you so much for the question.
Thank you very much.
Take care, guys.